Come on, my dears. Let us today finish this chapter. Still last two theoretical topics as well as one illustration is left out, and plus then after we will be going for MCQs in the exercise also. Okay. Now see the topic. The title of the topic is Thermonuclear fusion process in Sun and other stars. See, it is estimated that since 500 crores of years, Sun is continuously emitting radiant energy out of its surface with very high rate of emission, as high as 3.8 into 10 raised to 26 joule per second. Now tell me, how is it possible? Correct? How Sun is able to emit such an enormous amount of energy, and that too since 500 crores of years. Really, it became a puzzle for scientists all over the world for so many years from different branches. And among all the branches of science, nuclear physicists got very first success in explaining the root cause, the origin of this production of this energy. They could explain it very nicely, and that very process is only known as thermonuclear fusion process. What is called fusion process, that you know very well. Whenever two or more than two lighter nuclei combine, at that time the phenomenon of emission of energy is called fusion process. But here we call it thermonuclear fusion process because for such process to take place here, very high temperature is responsible. Correct? That's why we call it thermonuclear fusion process. How Sun is able to emit such an enormous amount of energy, I am showing you. At the core of Sun, temperature is approximately 20 into 10 raised to 6 Kelvin, that is approximately 2 crore Kelvin. 2 into 10 raised to 7, that is 2 crore Kelvin. And Sun is composed of hydrogen nuclei, that is protons. Correct? Now at this very high temperature, protons combine and they perform this fusion process. How? I am showing you. See, at this very high temperature, two protons combine. When two protons combine, the reaction you can write this way: 1H1 plus 1H1 gives 1H2 plus positron is emitted, 1 is 0, plus neutrino is emitted. Neutrino symbol is nu, and plus 0.42 million electron volt of energy is liberated. Here some mass is decreasing, and the decrease in mass appears in the form of energy. Okay. Then after this positron liberated here, positron, it associates with one electron. Then you may have question that from where this electron has come from. See, at this very high temperature, all the hydrogen atoms, they have lost their electrons, and that is why we have electron in taking part in this reaction. Okay. Come on, this positron emitted associates it with one electron, that is minus 1 is 0, then 1 minus 1, that is 0. So here it is a process of you can say annihilation. Annihilation means these two materialistic particles, they merge into each other, and that total mass is converted completely into energy, and that is why we have emission of 2 gamma ray photons. Because we have emission of 2 gamma ray photons, I am writing 2 into gamma, and plus 1.02 million electron volts of energy is liberated. Fine. Now this deuteron produced here, 1H2, combines with one more proton. 1H2 plus 1H1 gives you 2He3, and plus at the time 1 photon of gamma ray is emitted, plus 5.49 million electron volt of energy is generated. Now everywhere all the reactions are completely balanced, you can check it. 1 plus 1 that is 2, with atomic number 2 it is helium, and 2 plus 1 that is 3. Okay. Now when these three processes take place only one time, we have one nucleus like 2Ha3. But if these first three processes, if they take place two times, then we will have such a 2Ha3 nuclei. And now reaction takes place between them. 2Ha3 plus 2Ha3 gives you 2He4 plus 2 protons are emitted, 2 into 1H1 plus 12.86 million electron volt of energy is also liberated. Tell me, reaction is getting balanced here. 2 plus 2 that is 4, 2 into 1 that is 2, 2 plus 2 that is 4. Come on, 2 ones are 2, 2 plus 4 that is 6, 3 plus 3 that is 6. Okay, tell me, this in this whole cycle, when we started with 2 protons, we are getting 2 protons back with us. That's why we call this process as cyclic process, because from where you start, if you are coming back to the same state, then we call it cyclic process. So this is a cyclic process, but because we started with 2 protons, such a cyclic process is called proton-proton cyclic process. Proton-proton cyclic process. Okay, fine. Now, in this whole cycle, in this one cycle of proton-proton cyclic process, what is the total amount of energy liberated? I am showing you. Don't forget, in one cycle of proton-proton cyclic process, first three processes have taken place 2 times. So you must multiply all these amounts of energy by 2. That's what I have done here. This into 2, this into 2, this into 2. Okay. And in one cycle of proton-proton cyclic process, this fourth process takes place only once. So you can simply add this value, that is 12.86. When you add up all these values, the summation is exactly 26.72 million electron volt, which is very nearly equal to 26.7 million electron volt. This much energy is liberated per one cycle, and such many very large number of proton-proton cyclic process continuously go on the surface of sun, and that's why sun is able to emit such a very large amount of radiant energy with such a high rate, 3.8 into 10 raised to 26 joule per second. Tell me, ultimately in this process what has happened? When the lighter nuclei like proton and deuteron combine at high temperature, they form heavy nucleus like helium. At that time, phenomenon of liberation of energy is called thermonuclear fusion process. At very high temperature, when lighter nuclei like proton and deuteron combine, they form heavy nucleus like helium, and energy is emitted. This very phenomenon is called thermonuclear fusion process, correct? And because here we started with 2 protons, we call it proton-proton cyclic process. Okay. In other stars, there is one more cyclic process which is going on. That cyclic process is not in our syllabus. It is called carbon-nitrogen cyclic process. CN, carbon-nitrogen cyclic process. Here for sun, come on, it is which type of thermonuclear fusion process? Proton-proton cyclic process. Okay, fine. Now in textbook they have written that in one cycle of proton-proton cyclic process, 4 protons are consumed, 2 electrons are consumed, and we get, at the end of one cycle, we get 1 alpha particle, 2 neutrinos, and 6 gamma ray photons. How? I am showing you. See, first 3 process take place 2 times. So here number of protons you count 1, 2 and here 3. But because all the 3 processes are taking place 2 times, 3 2s are 6 protons are consumed. How many? 6 protons. And at the end we get 2 protons back with us. So 6 minus 2, that is net number of protons consumed in the process in one cycle is 6 minus 2, that is 4. Okay. Now this electron is there, and first 3 processes are taking place 2 times. So you can multiply this by 2. So 2 electrons are also consumed. At the end what do we get? At the end we get 1 alpha particle, that is helium nucleus, 2 neutrino, because this neutrino should be multiplied by 2 because first 3 process take place 2 times. So multiply this by 2, so I am getting here 2 neutrinos and 2 gamma ray photons here, 1 gamma ray photon here, 2 plus 1 that is 3 gamma ray photon, but don't forget first 3 process take place 2 times. So 3 2s are 6 gamma ray photons are also emitted. So at the cost of this many particles, we get 1 alpha particle, 2 neutrinos and 6 gamma ray photons. Got it? Fine. Now the nuclear physicists have predicted further that now onwards as time passes on, what will happen in future. Say suppose further 500 crores of years are passing, suppose. The nuclear physicists have made some calculations, and from those calculations they have made certain predictions. According to them, in coming 500 crores of years, it will so happen the total quantity of hydrogen nuclei that are accommodated right now in sun will be completely transformed into helium, correct? According to this thermonuclear fusion process. Fine. So after 500 crores of years, you will have only helium nuclei inside the sun, correct? Then no more combustion of hydrogen nuclei. So this combustion process would stop. Combustion process would stop. And as combustion is going on, at that time we have emission of heat energy. But if combustion has been stopped, then no more production of heat energy. So as time will pass further, what will happen? Sun will get cooled down. That's what I written here. Sun will get cooled down. And because of decrease of temperature, because of cooling process, you know, cooling is a cooling process induces compression. So because of cooling process, the sun will start getting contracted. Okay, compression process will continue. Fine. Then as the sun starts contracting, the temperature in the core will start increasing. And when temperature in the core is increasing, at that time it so happens that external layer, outermost layer of sun is now expanding, correct? And when the external layer, outermost layer is expanding, the radius would be becoming very large. Such a star is known as a red giant. What is it called? Red giant. Red giant is that star whose mass may be smaller than mass of sun or may be greater than mass of sun, but its radius is very large because of expansion of outermost layer. Such a star is called red giant. So our sun will get converted into red giant by that time. Okay, fine. And then after, as the temperature in the core increases, and suppose it becomes nearly equal to 10 raised to 8 Kelvin, then it will so happen that this helium nuclei will start getting converted into carbon nuclei through the same nuclear fusion process, correct? Through thermonuclear fusion process, helium nuclei will get start now getting converted into carbon nuclei. Fine. And then this is how the composition of sun would change, and then it changes from one type of star to another type of star, second type of star to third type of star. This process is called evolution of star. So sun will get evolved this way from one type to another type. Okay, so evolution would take place and it will continue. Okay, but the final elements formed after very large number of time, I mean very large number of years, after very large passage of time, it will so happen that final elements formed in the constitution of sun would not be having atomic mass number 56. They must be having atomic mass number less than 56, because we know atomic mass number with 56, it is the element called iron, and iron is most stable, correct? Here in this process what happens, that binding energy is increasing, so element is becoming more and more stable. But then if most stable element is iron, then that iron would not form. By these processes iron will not be formed, but you will have formation of those elements whose atomic mass number is slightly less than 56, correct? So unstable particles, unstable nuclei, they combine and they form stable nucleus, correct? But here already iron is most stable, so further process will not take place. Okay. Scientists all over the world, they are trying to obtain energy by controlled thermonuclear nuclear chain reaction process. Thermonuclear chain reaction process of fusion. That's what I written here. Controlled nuclear fusion chain reaction process. Controlled nuclear fusion chain reaction process. The way we saw last time, the nuclear chain reaction process for fission, same way we can have nuclear chain reaction process for fusion also, and from there also we can get energy, correct? Scientists over different countries, they are trying to obtain such energy, but till now not a great degree of success has been achieved, so far not achieved, correct? And scientists in India, they are trying to just work out for the same at one institute which is located at Bhat, which is a place near Ahmedabad, and one institute with name Institute of Plasma Research, shortly written as IPR, Institute of Plasma Research, where this process is under study. That process is controlled nuclear fusion chain reaction process. Controlled nuclear fusion chain reaction process. Got it? Fine. Now kindly read this statement of sum number 14. Read it? Fine. Look, here I have written one very small equation. Mass of sun is total number of protons inside it multiplied by mass of one proton. Because they have said in the statement that assume sun to be made up of only protons. Okay? So if mass of one proton is MP and such a number of total number of protons is NT, then when I multiply this mass by this number, I will get mass of entire sun, let it be Ms. Now find out Nt from here. It is Ms upon Mp, Ms upon Mp, mass of sun you are given in the statement 2 into 10 raised to 30 kilogram. What about Mp? Mass of proton, mass of one proton is 1.67 into 10 raised to minus 27 kilogram. And if you find out this answer, it is 1.2 into 10 raised to 57, that many number of protons. So total number of protons in the entire sun is 1.2 into 10 raised to 57 proton. And now energy obtained per second, it is also called power. Energy per unit time is called power. Let it be capital P. And that should be from the combustion of number of protons in unit time, and that number of protons which have been combusted per unit time is total number upon total time. Total number upon total time. Total number is Nt, total time is T. And what is the amount of energy liberated by combustion of one proton? That you are given in the statement 6.7 million electron volt. Convert it into electron volt, multiply by 10 raised to 6. But 1 electron volt is how many joule? 1.6 into 10 minus 19 joule. And now by this total time T, the all total number of protons would be getting combusted. Okay. So in what total time the total number of protons will get combusted, that is what we require to find out. This power of radiation from sun, they have given 3.9 into 10 raised to 26 watt. Watt means joule per second. This total number of protons we have found out 1.2 into 10 raised to 57. 6.7 as it is, 10 raised to 6 as it is, 1.6 as it is, 10 raised to minus 19 as it is. This T also as it is, which we want to find out. Find out value of T. In second it comes out to be 3.298 into 10 raised to 18 second. Leave proper gap, write small s, don't put any full stop. Now in the examination you may stop at this stage because you are asked to find out the time. But suppose you are asked to find out the time in year, then you know 1 year is 3.16 into 10 raised to 7 second. So going from year to second, you should multiply by 3.16 into 10 raised to 7. But speak reverse now. Going from second to number of year, you should divide by 3.16 into 10 raised to 7. And when you do that, final answer is 104.4 into 10 raised to 9 this many year. But 10 raised to 9 year means 1 giga year, giga, G-I-G-A, giga year, or it is also called 1 billion. 1 billion year means 10 raised to 9 year. Speak reverse. 10 raised to 9 year can be replaced by 1 billion year. So it is as good as 104.4 billion year. 104.4 billion year. Got it? Fine. Now let us see the last topic of the chapter about nuclear hazards or dangers of nuclear energy. See, whenever any scientist makes any research, he discovers anything, he invents anything, it is for the noble cause, it is for the welfare of the mankind. But later on, as time passes on, the mankind, it makes the destructive use also. That is the worst part of the story. When Mr. Otto Hahn and Strassmann had discovered this phenomenon of nuclear fission, at that time they might not be knowing that in the coming years, the scientists or persons all over world, they will make a destructive use of this atomic energy. They were not knowing at that time. Otherwise, they would not have invented such phenomena. But then we know nowadays all the developed countries, they have got enough number of nuclear weapons, and that number is such a large number. With that number of nuclear weapons, you can destroy this earth several times. You can destroy entire earth several times. That many nuclear weapons the developed country have. See, it is a really very sad story. Now, what is the danger part of this nuclear energy? When you are trying to obtain nuclear energy in the nuclear reactor, along with the production of the energy, we have lot of nuclear wastage also, lot of waste products. But all those nuclear waste products, they are full of gamma radiation. And this gamma radiation is most dangerous for all living beings. For human body, if you are talking about, if gamma radiation happens to pass through human body in a quantity beyond certain limit, you know what happens? All the complex molecules in our body, they get ionized. And if they get ionized, then they will not function anymore as they were functioning previously. And if it happens so, you know what will happen? Immediately that person would die. He would expire immediately. And if not so, then he would start suffering from madness. He may go mad. Then he may start suffering from physical abnormalities, some physical defects, some incurable disease also may enter in his body. And if by the incidence of this gamma radiation, if the genes are affected, then the worst results which are obtained due to this incidence of gamma radiation, they are continuing generation after generation. I can give you example for that. In the year 1945, on 6th August, morning 8:15 a.m., at this time, on this date, 6th August 1945, you must be knowing, the American government, American army had bombarded atomic bomb on Hiroshima, which is a town in Japan, correct? And at that time, the population of Hiroshima was nearly 350,000. And only in a very short time after the just attacking that nuclear bomb, immediately 70,000 people died. 70,000 people died immediately. And in the later 5 years, another 70,000 got died. See what a sad story. The energy which we are producing, that costs our life only. So we are a foolish one. If we are producing such an energy which will cost our life, we are a foolish one, I tell you. Now tell me, what is the danger part of that nuclear wastage? I told you, one more problem scientists are facing nowadays. No vessel is safe enough to store that nuclear wastage. No vessel is safe, correct? Then you cannot just put it into any container. Neither you can throw it in the ground. okay, in the soil you cannot throw it, because if the ground is just dig with, you are just digging the ground and if you are just inserting this nuclear wastage into that, then that land will become non-agricultural, correct? You cannot have any agriculture on that land. Then you cannot throw it in the sea also, otherwise all the sea life will be getting ruined up and the balance of this environment will be getting imbalanced, correct? You cannot throw it in air, you cannot make it contain in any container. Then what to do with the nuclear wastage is a great question which so far is not fully solved, okay? Then scientists are puzzled regarding the storage and disposal of this nuclear wastage. Then regarding explosion in reactor, if you don't take enough safety measure while carrying out this nuclear chain reaction process in nuclear reactor, it may cause explosion, and after that the surrounding region will be affected by leakage of gamma radiation. It is also very dangerous, and that same thing happened at Chernobyl in the country called Ukraine, correct, which is a part of Soviet Russia. It so happened that that in the reactor working at Chernobyl got exploded, and that had costed many lives also, correct. Then I told you all about the nuclear weapons with all the developed countries they have right now, and if the number of atomic bombs, I mean if you explode number of atomic bombs more than a certain number, then it will make the entire land all over the earth, which will not remain agricultural, it will become non-agricultural land, and then no other living being can exist in future, correct. So it will be unfit for all the lives on this whole earth, will become useless. And it is predicted by nuclear physicists that if this way the production of nuclear energy continues, then we will have such a huge quantity of nuclear wastage that after some years we will have collection of nuclear wastage might be hanging in air in the form of a cloud, and that cloud would simply absorb the solar radiation and will not allow that solar radiation to come to us on the earth. Then naturally on the earth we will have winter season, that too permanently, which is called nuclear winter. Let us hope for the good now. We all unanimously should think for this very seriously, and let us pray to God that coming time should be more safer. Come on now, let us begin with exercise MCQs. Kindly read the statement of first MCQ. Read it. Look, very simple question. The element given to you is 82 Pb 206. Just compare it with ZXA. Then what is Z? Come on, 82. Number of protons is 82. What about atomic mass number? A equals to 206. And you know atomic mass number also gives you total number of protons and neutrons. That is total number of nucleons. What about number of neutrons? It is given by formula A minus Z. So it is 206 minus 82. Answer is 124. But you must answer as per the order of questions. In the first question they have asked number of protons, which is 82. In the second question they have asked number of neutrons, which is 124. And in the final question they have asked number of nucleons, which is 206. So please answer in this order, okay. It is not only important to get the correct answer, but you must place them. If more than one questions are asked, you must place the right order of the answers also, okay. Now kindly read the second statement. Read it. The given nucleus is 6, say 12, and now out of given other nuclei, which is isotope of this, which is isotone for this, which is isobar for this, that is what we have to find out. For isotopes, you know, atomic number is same. So if here atomic number is 6, then here also it must be 6. And with atomic number 6, what is the element in the periodic table? Carbon. And isotopes have different atomic mass number. You can see here it is 12, here it is 14. So now this becomes isotope for this, okay. What about isotone? In case of isotones, number of neutrons is same. So that is n equals to same, that is A minus Z must be same. What is A minus Z here? 13 minus 7, that is 6. And here also 12 minus 6, that is 6. So number of neutrons is same here and here. Hai? So these two are called isotones of each other. What about isobars? Come on, in case of isobar, atomic number is different, atomic mass number is same. What is atomic mass number here? 12. And here also it is 12. Here atomic number is 6, here it is 5. With atomic number 5, in the periodic table we have element called boron. So these two have same atomic mass number but different atomic numbers. They are called isobars of each other. These two are isotopes of carbon, these two are isotones of each other, and these two are isobars of each other. Got it? Fine. Now tell me, read the statement of number 3. Read it. 13 aluminum 27. So what is the atomic mass number here? 27. Let it be A1. What is the second nucleus? 30 zinc 64. So what is the atomic mass number here? 64. So I am taking it as A2. And now don't you know, the characteristic or average radius of nucleus is directly proportional to cube root of atomic mass number, or proportional to A raised to 1 by 3. When it is direct proportionality, then you take 1 to 1 2. So R1 upon R2 equals to here A1 raised to 1 by 3 upon A2 raised to 1 by 3. Come on, what is A1? A1 is 27 raised to 1 by 3. A2 is 64 raised to 1 by 3. 27 raised to 1 by 3 is 3. 64 raised to 1 by 3 is 4. And now tell me, R1 upon R2 equals to 3 by 4. In examination, they may ask R2 upon R1. They may ask R2 upon R1, then it may be 4 by 3 at the time. You please read the question, what have they asked, okay. Here they have asked R1 upon R2, so answer is 3 by 4, okay. Come on, read now number 4. Read it. 1H2 plus 1H2 gives you 2He4. This is the reaction, okay. Out of 2 deuterons, we get helium nucleus. Fine. Let us find out total binding energy in the initial condition, that is before the reaction. Total binding energy, if you want, then you should multiply total number of nucleons multiplied by binding energy per 1 nucleon. Binding energy per 1 nucleon, they have given 1.1 million electron volt. And what is total number of nucleons before the reaction? This 2 plus 2, that is 4. 4 into 1.1, answer is 4.4 million electron volt. Okay, fine. What about total binding energy in the final condition? Let it be EF. That is binding energy per 1 nucleon in the final condition multiplied by total number of nucleons in the final condition. Total number of nucleons in the final condition is 4 and binding energy per one nucleon they have given as 7 million electron volt in the final condition. 7 4s are 28 million electron volt. What was initial binding energy? 4.4. What is final binding energy? 28. So you can see this number is greater than this number. So EF is greater than EI. When EF is greater than EI, remember in any nuclear reaction, if final binding energy is more, it wants to say that final nucleus is more stable. When any nucleus will become more stable, provided it emits excess of energy. So in any nuclear reaction, whenever you find that final binding energy is more, it means to say that that process is, exorgic, in which energy is emitted. Okay. So in this process also energy will be liberated. But how much energy will be liberated? If you want to find out that, you just subtract smaller value of energy from bigger value of energy. Bigger value of energy is 28 million electron volt, smaller value is 4.4 million electron volt. 28 minus 4.4, answer is 23.6 million electron volt. Okay. Whenever EF is greater than EI, remember energy will be liberated. Now speak reverse. If EF is less than EI, then energy will be absorbed. That process is called endorgic process. Right now this is exorgic process because energy is emitted. Fine. Now read number 5. Read it. All those elements are said to be naturally radioactive whose atomic mass number is greater than 206. I am talking about atomic mass number. But here if you are talking about atomic number, it is found to be greater than 82. But among 4 options you don't find Z greater than 82. But with one option it is found to be correct, Z greater than 83. Naturally, if Z is greater than 83, it has to be greater than 82. So what I said is also right and what is they have given is also correct. Z greater than 83. All such elements are naturally radioactive. Read number 6 now. Read it. If you remembered, in this chapter we had compared the properties of radioactive radiations, and in that I told you alpha particles or alpha radiation has maximum ionization power. So alpha particles have maximum ionization power. Remember. Read number 7 now. Read it. As time would pass, the activity will go on decreasing exponentially. According to this law, we know it is exponential law. I equals to I0 e raised to minus lambda t. Bring this term down, so it is I0 upon e raised to plus lambda t. You can see here, these 3 parts are constants. So as time would pass, this activity will go on decreasing. Not only that, it decreases exponentially. So as time passes on, activity goes on decreasing. This is written here, activity decreases, but so far lambda is concerned, lambda would remain constant because lambda is called radioactive constant, which is a constant for a given radioactive element. As long as radioactive element remains same, there won't be any change in the value of lambda. So activity decreases, but lambda remains constant. That is the final answer. Okay, fine. Read number 8 now. Read it. Given time is t equals to n into tau half. Suppose given time is suppose n times half life. Given time is 20 minutes and we want to find out half life. They have given 5 minutes. Mind well, both these times must have same unit. Come on. Now find out n. 20 upon 5, that is 4. M equals to m0 upon 2 raised to n. You know, at the end of time equal to n times half life, the mass of undisintegrated element is m0 upon 2 raised to n. m0 as it is 2 raised to n, but what is the value of n? It is 4. Now 2 raised to 4 is 16, and now 1 upon 16, that answer is 0.0625, 0.0625 into m0. Wait, if they are expecting the answer in percentage, you must multiply this by 100%. So it is now 6.25% m0. Remember, this is undisintegrated mass. This is undisintegrated mass, and if in the examination they ask about disintegrated mass, then you should subtract m. You should take m0 minus m. You should take m0 minus m. You should subtract m from m0. If you take m0 to be 100% minus m, which you have got 6.25%, so 100 minus 6.25, that will be 93.75%. But that is disintegrated mass. Right now what they have asked, undisintegrated mass, which is 6.25% of initial undisintegrated mass. Got it? Now kindly read this statement of number 9. Read it. T equals to n into tau half, but given time is right now 3 times the half life. Given time is 3 times the half life, that is what they given in the statement. So if you match these two, you will get the value of n equal to 3. N equals to 3. And now at the end of this much time, you know whether it is activity or mass or number, that would become 2 raised to nth part. That would become 2 raised to nth part of the initial value. Come on, here I equals to I0 upon 2 raised to n, but 1 upon 2 raised to n, value of n is 3. Value of n is 3. Okay, just put n equal to 3 and just bring it out. 1 upon 2 raised to 3 into I0. Just take it on the one side, 1 upon 2 raised to 3 into I0. So this activity has become 1 upon 2 raised to 3 times this initial activity. Similarly, this undisintegrated mass has become 1 upon 2 raised to 3 times initial undisintegrated mass. Similarly, this undisintegrated number of atoms has become 1 upon 2 raised to 3 times this undisintegrated number of atoms initially. Got it? If they are asking how many times, then answer is 1 upon 2 raised to 3. If they are asking what part, then the answer is only 2 raised to 3. I repeat, if they are asking how many times, then you should take this multiplying factor, which is 1 upon 2 raised to 3. If they are asking what part, then you should consider only denominator, that is 2 raised to 3. Correct? Now kindly read this statement of number 10. Read it. Tell me what is the original element. Original element is 94 plutonium 241. 94 plutonium 241. Wait. Now tell me the number of alpha particles emitted. Number of alpha particles emitted, I am taking X, which they have given in the statement as 8. Number of beta particles emitted, I am taking Y, which they given in the statement as 5. I told you to remember the atomic mass number and atomic number of new element. Remember, formula was A dash equals to A minus 4X, where A is the atomic mass number of original element. Atomic mass number of original element is right now 241 minus 4 into X. X they are given as 8. Answer is A dash equals to 209. What about atomic number of new element? It is Z dash. I told you to remember that formula also. Z dash equals to Z minus 2X plus Y. Z is 94. Atomic number of original element minus 2 into X. They are given 8. Y they have given as 5. Simplify, answer is 83. What about new element? It should write Z dash, and with Z dash, what is the atomic number right now? 83. With 83, come on, the element in the periodic table is none but bismuth. And what about atomic mass number? It is 209. So new element is our final answer, 83 bismuth 209. 83 bismuth 209. Now kindly read the statement of number 11. Read it. Come on. M equals to M0 into e raised to minus lambda t. This undisintegrated mass they have given at the end of 2 days. How much? 1 upon 3 gram. And this initial mass is 1 gram. And this thing happens at the end of how many days? At the end of 2 days. So value of t is 2. So it is e raised to minus 2 lambda. E raised to minus 2 lambda. Leave it. Now I just change this undisintegrated mass symbolically from m to m dash, and new time I am taking instead of t, I am taking t dash. New time then new mass. Okay. Now this initial mass they have given 1 gram into e raised to minus lambda into t dash. New time they have given as 6 days. So put the value of t dash as 6. So e raised to minus 6 lambda. E raised to minus 6 lambda. Can you rewrite this term as e raised to minus 2 lambda whole raised to 3? Can you write? Now tell me, what is value of e raised to minus 2 lambda? It is 1 by 3. So this value is 1 by 3 whole raised to 3. Now 1 cube is 1 only, 3 cube is 27. So what is it? 1 upon 27 gram. But remember, this is undisintegrated mass at the end of 6 days. If they ask about disintegrated mass, then you should find out M0 minus M dash. M0 was 1. 1 minus 1 upon 27, that would be answer 26 upon 27. 26 upon 27, that many gram. If they are asking disintegrated mass, right now they have asked undisintegrated mass. Okay. Kindly read the statement of number 12 now. Read it. Come on, for this nucleus P, they have given binding energy per one nucleon as X. Come on, binding energy for this nucleus per one nucleon they have given as Y. This value is different than this, so I am giving different symbol E, B and dash. And now the reaction which they have given is ZPN plus ZPN gives Z dash Q2N. This is the reaction they have given. This is the part before the reaction, that is initial condition, and finally this is the nucleus. Okay, these are the reactants, this is the product. Now tell me, what is total binding energy in the initial condition? that is binding energy per one nucleon in the initial condition multiplied by total number of nucleons. Come on, binding energy per one nucleon in the initial condition they are given as x, and total number of nucleons you can see n plus n, that is 2n, correct? What about total binding energy in the final condition? Let it be EF. Again it is binding energy per one nucleon in the final condition which they have given for Q nucleus as y. So this binding energy per one nucleon is right now y, and multiplied by total number of nucleons in the final condition. Total number of nucleons in the final condition is 2n. And so far Q value of the reaction is concerned, it is always to be found out this way, EF minus EI, EF minus EI. But what is value of EF? 2ny minus value of EI is common 2nx, correct? But remember this is Q value of reaction. If Q is less than 0, then only you can say this is the amount of energy which has been absorbed. And if the amount of energy is absorbed, then value of Q must be negative. If value of Q has to be negative, then they must give in the statement x greater than y. So if they have not given x greater than y in the statement, it is wrong, you must write, okay? See, if x is less than y, then this subtraction would be positive. And if Q value is positive, energy is not absorbed, energy is liberated. So if they have asked absorbed amount of energy, then this Q value must come out negative, and for that required condition is x must be greater than y. They must have given in the statement. If they have not given, you may add it, okay? Fine. Come on now, read the statement of number 13. Read it? Come on. According to exponential law for radioactive disintegration, don't you know the formula? N equals to N0 into e raised to minus lambda t. Fine. Suppose the time interval which has been lapsed is T1, and at the end of this much time, number of undisintegrated atoms is suppose N1. Similarly, at the end of T2 time, the number is N2. Okay, fine. Now, T2 is the later time. Later time is always greater. So, T2 is greater than T1. Because T2 is greater than T1, you know, in a radioactive element, as time passes on more and more, the number of undisintegrated atoms decreases. So, as compared to this number is less. So, that's why written here N2 less than N1. Correct? Now, we are asked to find out that number of disintegrated atoms which have been disintegrated in the time interval between these two instants. Between these two instants, the time interval lapse is T2 minus T1. T2 minus T1. In that much time interval, what is the number that has been disintegrated? That number is nothing but this minus this. Correct? Suppose initially it is 100 and later on it is 40 suppose. So initially it was 100, now left is 40. So what is the number that has been disintegrated? It must be 60. How could you get 60? 100 minus 40. That is this minus this. Correct? So our answer is N1 minus N2. And when you want N1 minus N2, directly you can go for subtraction. This minus this. So I have written here N1 minus N2 will be equal to this minus this. N0, N0 common, inside the bracket this minus this, e raised to minus lambda T1 minus e raised to minus lambda T2. Got it? This is your answer. Okay. Now kindly read this statement of number 14. Have you read it? Tell me. We had studied about branch disintegration in which given radioactive element simultaneously emits both alpha particle also, beta particle also. At that time, how would you find out effective half-life? For that, this was the formula. Remember, 1 upon tau half equals to 1 upon tau half for alpha emission plus 1 upon tau half for beta emission. This value they have given in the statement as 4 year. This value they have given in the statement as 12 year. Find out, you will get value of tau half as 3 year. Okay. Don't you know this formula? At the end of this much time equal to n times half-life, the activity would remain, come on, I0 upon 2 raised to n. Do you know that formula? Come on. This total time given to you is 12 year. N value I want to find out, tau half. We have found out it is 3 year. Mind well, both these times must have same unit. And now n comes out to be 12 upon 3, that is 4. Now at the end of this much time, the activity of a radioactive element is I0 upon 2 raised to n. I0 as it is, 2 as it is, but n value is 4. But 2 raised to 4 is how much? It is 16. And 1 upon 16 comes out to be 0.0625 into I0. But if you want this activity in percentage, you must multiply by 100%. So multiply this value by 100%, you will get the answer 6.25% of I0. But remember, this is the activity which has been left out at the end of this much time, at the end of 3 years, at the end of 3 years, sorry, at the end of total time, that is 12 years. At the end of 12 years, this much activity is left out, okay. But if they ask, what is the activity that has been decreased, then out of 100%, you should subtract this, then answer would be 93.75% of activity has been decreased at the end of 12 years. And what is the activity which has been left at the end of 12 years? That answer is this 6.25% I0, correct? So please read the question, what is really asked, okay? Now kindly read the statement of number 15. Read it. Now out of 3 given substances, which substance is used as a moderator, which one is used as a coolant, and which one is used as a controlling rod? You know very much. Come on. Graphite is used as a moderator, liquid sodium is used as a coolant, and cadmium rod is used as a controlling rod, correct? Along with this, you please try to recall other names also. As a moderator, which 4 substances are normally used? Simple water, that is H2O, heavy water, that is D2O, carbon in the form of graphite, and beryllium. Remember, for coolants, come on, water, gases, liquid sodium, liquid lithium, etc. What about controlling rods? They might be made up of cadmium also, might be made up of boron also. Remember na? Fine. Now go for 16. Read the statement. 13 aluminum 32, that is what is the reactant, the element or the nucleus which we have initially. It disrupts and it gets transformed into 13 aluminum 27. That is what they have given in the statement. Now during this process, which of the particles given to you in the 4 options can be emitted? They have given wrong answer as a proton. But whatever it may be, proton can't be emitted here because look here, atomic number remains same. When atomic number remains same, it must be emitted particle which is neutron. Neutron must have been emitted, which doesn't cause any change in atomic number. Okay, when atomic number is remaining same, it must be neutron. But not only 1 neutron, 5 neutrons must have been emitted that's why I am writing 0 and 1, that is 1 neutron multiplied by 5, because 5 into 0, 0, 0 plus 13 will be 13 only, but 5 into 1, that is 5, and 5 plus 27 should be 32, correct? So 5 neutrons must have been emitted. In the textbook, answer is wrong, correct answer is neutron, okay? Now read number 17. Read it, look. Here I am writing the values for element A, here I am writing values for element B. Come on, at time t equal to 0, initial activity of element A I am taking I0, for B also I am taking I0, because they have given in the statement that their initial activities are same. Now at the end of 2 hours, which is the half-life for element A, naturally if you allow the time equal to half-life, activity will be reduced to half of initial value. Half of this is I0 by 2, correct? You need not to write any value here, okay? We don't require that. Now allow another 2 hours to get lapse. So 2 plus 2, that is total time lapse is 4 hours. Now 2 hours is nothing but half-life for element A. So again that number or activity will reduce to half. Half of this will be I0 by 4. But right from beginning, what is the total time that has been lapsed? That is 4 hours, and 4 hours is the half-life for element B. If you allow time equal to half-life to get lapsed, naturally activity will be reduced to half. Half of this is I0 by 2, correct? So in short, at the end of 4 hours, the activity of element A is this much, and activity of element B is this much. And now at the end of 4 hours, if I require ratio of activities of both the elements IA upon IB, then tell me what is IA value? I0 by 4 divided by IB is how much? I0 by 2. I0 will cancel. Denominator will become numerator. So it is 2 by 4, which is 1 by 2 or 1 is to 2. 1 is to 2, correct? So our answer is IA upon IB equals to 1 upon 2 or 1 is to 2. Got it? Kindly read the number 18. It's a very good question. Huh? Come on, read it. Tell me, what have they given? In one box which is enclosed from all the sides, there is some radioactive element which emits alpha particles. Okay? The initial number of undisintegrated atoms in that element, they have given 1 mole. 1 mole means 6.02 into 10 raised to 23 atoms. Okay? Kindly apply exponential law. N equals to N0 into e raised to minus lambda t. Now at the end of t time, the number left is n. And what must be that number? Initial number minus number of alpha particles that has been emitted. Initial number is 1 mole. 1 mole is how much? 6.02 into 10 raised to 23. Now it so happens that at the end of certain time, this many alpha particles are collected in that enclosed box. Come on, what is the number they are given? 4.515 into 10 raised to 23. Now the emitted alpha particles, if they remain inside the box, then it must be, you can say that in that much time, this element which has been put in the box must have emitted that many alpha particles. So that many number will get reduced in the undisintegrated number. So initially undisintegrated number was this much, 1 mole, and now minus that number of alpha particles which have been disintegrated, and which number of alpha particles emitted is this much, meaning thereby this much number gets reduced in the original number. Original number was this much, minus this number is 4.515 into 10 raised to 23. Fine. N0 is initial number of undisintegrated atoms, and that is given to you 1 mole. 1 mole means 6.02 into 10 raised to 23 into e raised to minus lambda t. Got it? Let me explain once again. This is the number of undisintegrated atoms which are left inside that box at the end of t time. Okay? That number is how much? See, initial number is this much, 6.02 into 10 raised to 23, that is 1 mole. And now in a particular time t, it has emitted this many alpha particles. Okay? So meaning thereby this much number of undisintegrated number of atoms will decrease. This much number will get decreased in the number of undisintegrated atoms. So out of this initial number you may subtract this, and then the number left at the end of t time will be this minus this. And right hand side I have explained, come on, N0 is initial number which is 1 mole, 6.02 into 10 raised to 23 multiplied by e raised to minus lambda t. Throughout the equation what you can cancel? 10 raised to 23, 10 raised to 23, 10 raised to 23, you can get it cancelled. Now left is this minus this, I have written here, this minus this, and this factor you can just transfer in the denominator on left side divided by 6.02, and that equals to e raised to minus lambda t, correct? Now this minus this, answer is this much divided by 6.02, and this factor you can just bring it down from power, earlier it was minus, now it has become plus, and now this upon this, answer is 1 upon 4, right hand side as it is, take cross multiplication, so e raised to lambda t equals to 4, e raised to lambda t equals to 4, take natural log on both the sides, that is logarithm to the base e, when you take log here, this power will become multiplier, lambda t into natural log of e, and here when you take natural log, you know base e to base 10, you must multiply by 2.303, so it is 2.303 log of 4. Now this lambda formula you know, it is 0.693 upon tau half into small t as it is, natural log of e means what? Log e base e, which is 1. 2.303 as it is, come on, log 4, from our log table to the base 10, we know the log of 4 value is 0.6021, 0.6021, and now simplify. Now come on, tau half, that is a half life which is given to you 5 hour. If you are taking this time in hour, naturally this time will be obtained in hour. So this half life is 5 hour, rest of the values as it is, this into this comes out to be this much. Okay, now find out time t, you will get it in hour, the value is 10.00459 this many hour, but this is nearly equal to 10 hour, nearly equal to 10 hour. Got it? Now read number 19. Read it? Come on. This is the reaction which they have given. Okay? Come on. We call it sometimes radioactive series. Radioactive series. Okay? Come on. Series of some elements which are radioactive they have given. Now we are asked to find out the right order of emitted particles. Firstly, which particle is emitted? Secondly, which particle? Thirdly, which particle? Like that. Okay? Now you can see here there is increase in atomic number by 1 unit, atomic mass number does not change. It must be beta negative, beta negative. During the emission of beta negative or during the emission of electron, you know atomic number increases by 1 unit, atomic mass number does not change. So first emitted particle must be beta negative. Secondly, you can notice from this atomic number it becomes this much. If you subtract 2 from here, you will get Z minus 1. And if you subtract 4 from here, you will get A minus 4. So in this disintegration, the emitted particle must be alpha particle. Then only atomic number decreases by 2 units and atomic mass number decreases by 4 units. That's why I am putting here alpha particle. And the last particle emitted must be beta negative, because once again, if you add 1 here, from this you will get Z. And come on, atomic mass number remains same. If atomic number increases by 1 and atomic mass number does not change, the emitted particle must be beta negative. So last emitted particle is beta negative. So what is the right order? beta negative, comma, alpha, comma, beta negative. Got it? Fine. Now kindly read the statement of number 20. Read it? Fine. Again they have given one series of radioactive elements, one reaction they have given, and they have asked which are the isotopes in this series. Let us find out. For this initial nucleus, I am just assuming, come on, atomic number is Z and atomic mass number is A. Firstly, it emits, come on, alpha particle. During the emission of alpha particle, atomic number decreases by 2 units, atomic mass number decreases by 4 units. So subtract 2 from here, you will get Z minus 2. Subtract 4 from here, you will get A minus 4. Secondly, it is beta negative. During the emission of beta negative, you know atomic number increases by 1 unit, atomic mass number does not change. So this will increase by 1 unit, Z minus 2 plus 1, that is Z minus 1. And this atomic mass number does not change. Again, beta negative is emitted. Again, same story. This atomic number will increase by 1 unit, Z minus 1 plus 1 will become Z. Atomic mass number does not change. Now tell me, what are called isotopes? Atoms for the nuclei of which atomic number is same but atomic mass number is different are called isotopes of given element. Here you can see, come on, atomic number is Z. Here also atomic number is Z. So if atomic number is same, they are said to be isotopes of a given element. So right answer is, come on, for isotopes, it must be X and X3. Come on, isotopes must be X, comma, X3. Okay, fine. Now number 21. Read number 21. Read it? Tell me. Here I am writing number of undisintegrated atoms in element X. Here I am writing in element Y. Now, if you take X element as parent element and if you take Y element as daughter element, the number of atoms in parent element will go on decreasing, but number of atoms in daughter element will go on increasing. So, number of atoms in element Y is nothing but N0 minus Nx, N0 minus Nx. As this goes on decreasing, this subtraction would go on increasing. Come on. What is the, at time t equal to 0, at the beginning moment, the number of undisintegrated atoms in element X is suppose N0. Now when you place Nx equal to N0 here, to put it here, Nx equal to N0, then N0 minus N0 will be 0. Now you are asked to find out ratio of, come on, number of undisintegrated atoms in element X to number in Y. Now tell me, Nx upon Ny, if you find out here, this upon this, that is this upon this, N0 upon 0 is infinity. Something upon 0 is always infinity. Now at the end of 3 hours, what is 3 hours? It is half-life for element X. Naturally, if you allow time equal to half-life, number will be reduced to half. Half of this, that is N0 by 2, correct? Put Nx equal to N0 by 2 over here, N0 minus N0 by 2, left is N0 by 2, correct? Now take the ratio of Nx upon Ny, that is this upon this, that is this upon this will be 1. Again allow same time, same half-life, that is 3 hours. 3 hours plus 3 hours, so total time left is 6 hours. At the end of time equal to half-life, number will be reduced to half. Half of this is N0 by 4. And now put Nx equal to N0 by 4 here. So N0 minus N0 by 4, that is 3 N0 by 4. And now you are asked to find out Nx upon Ny. Come on, this upon this, that is this upon this. So when you take this upon this, answer is 1 by 3. Okay. Allow another 3 hours. then 6 plus 3, that is 9 hours. Then number will be reduced to half, because 3 hours is half life for element X. So half of this will be N0 by 8. Put Nx equal to N0 by 8 over here. N0 minus N0 by 8, that is 7 N0 by 8. And find out this upon this, answer is 1 by 7. And finally, allow another 3 hours. So 9 plus 3, that is total time lapse is 12 hours. At the end of time equal to half life of element X, number in that element will be reduced to half. So half of this will be N0 by 16. And put Nx equal to N0 by 16 over here, correct? Then you get Ny equal to N0 minus N0 by 16, which is 15 N0 by 16, correct? And now find out this upon this. When you find out this upon this, answer is 1 upon 15. Now what have they asked really in the statement? At the end of what time the ratio of number of undisintegrated atoms in element X to element Y would become 1 upon 15. The time we know now, the time is none but 12 hours. So final answer is T equal to 12 hours. At the end of this much time, the ratio of number of undisintegrated atoms in element X to element Y would be 1 upon 15. Got it? Kindly read the statement of number 22. Read it? Tell me. According to Einstein's mass energy conversion relation, don't you know E equals to mc square? But instead of m, I am just putting here delta m. So equivalent energy is E equals to delta m into c square, where delta m is called mass defect, which at present they have given 0.5% of 1 kilogram of hydrogen. Come on, I am writing 1 kilogram, but it's a 0.5 percentage. How would you find out? Multiply by 0.5, divide by 100. How would you find out 0.5 percentage? Multiply by 0.5, divide by 100. What about velocity of light in vacuum? 3 into 10 raised to 8 meter per second, and it's a square. And now simplify, answer is 45 into 10 raised to 13, that many joule. But wait, in first semester you had studied that 1 kilowatt hour is nothing but 3.6 into 10 raised to 6 joule. So while going from kilowatt hour to joule, you will multiply by 3.6 into 10 raised to 6. Now speak reverse. You are going from joule to kilowatt hour, then you should divide by the same factor. That's why the same value I am dividing by 3.6 into 10 raised to 6. Correct? Now this upon this, answer is 1.25 into 10 raised to 8. That many kilowatt hour. And in first semester, you were calling this kilowatt hour as 1 unit of electrical energy. So you may call this many kilowatt hour or this many units of electrical energy also, no problem. Now read statement of number 23. Read it? Come on. Again they have given one such reaction and they have asked the atomic number and atomic mass number for the last element. Let us find out. Initially for the first element, I am taking atomic number and atomic mass number they have given in the statement. Atomic number they have given 72, atomic mass number they have given 180, element is X. Firstly it emits alpha particle. When it emits alpha particle, atomic number will decrease by 2 units and atomic mass number will decrease by 4 units. Come on, 72 minus 2, that is 70. Element they have given X1, this minus 4 will be 176. After that it emits beta particle. During the emission of beta particle, atomic number would increase by 1 unit. So 70 plus 1, that is 71. Atomic mass number does not change. Then after it emits alpha particle. During the emission of alpha particle, atomic number will decrease by 2 units, atomic mass number will decrease by 4 units. So subtract 2 from here, it will be 69, and subtract 4 from here, it will be 172. And lastly, gamma radiation is emitted. During the emission of gamma ray, you know, atomic number and mass number does not change. Atomic number does not change, atomic mass number also does not change. So 69 as it is, 172 as it is. In the textbook they have given here x3 and here x4, that's why I am writing x3 and x4. Otherwise, let me tell you, during the emission of gamma ray, the type of element does not change. So these two elements are same. So you may write here x3 also, no problem, because elements are same, correct? But this is excited and this is unexcited. Okay, fine. Now tell me, for the last element which they given by symbol x4, what is the atomic number? 69. And what is the atomic mass number? 172. Okay, fine. Now kindly read the statement of number 24. Read it. What have they given? For element X, it's a half-life, and for element Y, it's a average life. They have given equal. Half-life of element X and average life of element Y are equal. Don't you know formula of half-life? Tau half is 0.693 upon lambda. Because we are talking about element X, I am putting here lambda X. And formula of average life is what? Tau equals to 1 upon lambda. Here element Y, then here also lambda Y. Got it? Find out lambda Y, it will be lambda X upon 0.693. And if you find out 1 upon 0.693, it comes out to be 1.443 into lambda X. But this multiplier, you can see it is greater than 1. Because this is greater than 1, lambda Y is greater than lambda X. Fine. Now tell me, what is the formula for activity? I equals to dN upon dt, and dN upon dt equals to minus lambda n. In short, I equals to minus lambda n. You talk about initial activity, then I0 will be minus lambda n0. I0 equals to minus lambda n0, correct? Write the same equation for element Y. So I am writing here I0y minus lambda y n0y. Write the same equation for element X. Come on, I0, instead of y you just write x, instead of y x, instead of y x. Okay. Now just take the ratio I0 of y upon I0 of x. If I am taking, then this upon this, minus minus will become plus. Come on, lambda y upon lambda x I have written, because the initial number of undisintegrated terms in both the elements, they have given same in the statement. Because these two numbers are same, come on, their ratio would be 1. And now this we have proved greater than this. Lambda y is greater than lambda x. If lambda y is greater than lambda x, if this numerator is greater than this denominator, means this numerator must be greater than this denominator. So I0 of y must be greater than I0 of x. That is, initial activity of element y must be greater than initial activity of element x. Correct? Fine. Now kindly read the statement of number 25. Read it? Come on. N equals to N0 e raised to minus lambda t. You are talking about first element, write here lambda 1, and here write N1. You are talking about second element, write here lambda 2 and here N2. And why no change here? Because they have given initial number of undisintegrated atoms in both the elements as same. These two values are same. Okay. Now radioactive constant for first element they have given as 10 lambda, and radioactive constant for second element they have given only lambda. Take the ratio now. N1 upon N2 will be equal to this upon this, N0 will cancel. e raised to minus 10 lambda t divided by e raised to minus lambda t. Okay, and now take this up. When you take it up, this power instead of minus it will become plus. Now e raised to minus 10 lambda t plus lambda t, minus 10 lambda t plus lambda t, how much it is? Minus 9 lambda t. That's what I written here, e raised to minus 9 lambda t. But just bring it down, then 1 upon e raised to plus 9 lambda t. Got it? And now this ratio they have given as 1 upon e. In the statement they have given this ratio as 1 upon e. This part as it is. Come on, numerators are same, so you can compare the denominators. And in the denominators also these bases are same, so these powers also must be same. Here power is 1, here power is 9 lambda t, so 9 lambda t must be equal to 1. If 9 lambda t equals to 1, then what is t? 1 upon 9 lambda. So required time is, come on, answer is 1 upon 9 lambda. Got it?